Hello, yo, welcome back. All right, so we are going to be looking at part 2 of Laplace transform. Laplace transform part 2. Okay, so in this series of videos, we're going to be discussing Heaviside unit step function. So, what is a Heaviside unit step function? Now, Heaviside unit step function is actually a function of time, okay, in which such a function, right, turns on another function at a particular interval of time. Now it is denoted as f of t equal to u of t minus c. This is the expression. Okay, so now u of t minus c. Now the c is the shift or the time. All right, the time at which the function actually turns on. Now in this case, this is the coefficient, of course, of the function is 1. That simply means that the function, all right, can actually output 1 when t is equal to c. But when t is less than c, when t is equal to c and of course and above, it will output 1, being the, of course, the coefficient of this particular function. Then when t is less than c, it will turn the function off. It will actually output 0. Now look at it. So what we have, all right, as an effect of unit step function is that in this case, when f of t is equal to 0, it will output 0 at any value of t that is less than c, when t is less than c. Okay, but it will always output 1 when t is greater or equal to c. So immediately the time actually reaches c, all right, and above, then what happened? The function actually output 1. So just look at a unit step function as an on or off switch that transfers input voltage to the output. All right, so when the switch is off, it outputs 0 to the output. When the switch is on, right, then it will actually transfer the entire input voltage to the output voltage. So please take note of that. So invariably now, in this case now, what the function is actually outputting is 1 when t is greater or equal to c. What if we have it this way? F of t, all right, of course, being equal to, let's say, a constant value, a u of t minus c. So what do we expect here? Of course, you know exactly what we expect here. So in this case, we will have that, of course, the function will actually is equal to 0 at any value of t that is less than c. But the function will output the entire a, all right? F of t will be equal to a at any value of t that is greater or equal to c. So please take note of that. That is a unit step function. So now, not just a constant, the function does not actually output a constant value, all right? It can also output another function. For example, if the f of t we are looking at is actually equal to t square, let's say t square, then u of t minus c. What do we expect? Okay, what do we expect at this point? Because u of t will definitely be 1 at any value of t greater or equal to c. That will enable it to output t square. So invariably in this case, okay, it is also applicable. All right, we can have that f of t is equal to 0 for any value of t less than c, but f of t will actually be t squared. The entire function will be outputted t squared, okay, when the value of t is greater or equal to c. So I hope that is well understood. So we can actually present that in a graph. So let's say, of course, this is actually, let's look at a graph of t squared, see how this unit step function actually changes the graph of t square when it is actually applied to it. Ordinarily, the graph of t square, of course, is a quadratic, okay, more like a parabolic form. Okay, so this is how the graph actually goes normally. So of course, this is the graph of t square. Now, when this particular graph, of course, is actually being passed through a unit step function at, okay, an interval of course t being equal to c, then you know exactly what will happen. Okay, so the output we'll get is such that at the point where t, let's say this is the point, okay, at the point where t is equal to c, that is the only point the function, okay, will be on. So every other part of this function that is less than c will be cut out. So invariably, I can actually use a dotted line to represent that. That means dot 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 dot, the function becomes off until you get to the point where, all right, the time is, of course, this is the time as is, and this is f of t. Okay, this is the time as this, and of course this is f of t. So it is at this point that the function will actually turn on. So let me use a different color. Okay, so it is only the part that is not taken out is only this part. Every other part of this particular function of this graph is actually eliminated. I hope that is well understood. So we can also look at that of the unit step function. Okay, we're going to look at the unit step function of the sine of t, sine t, then u of t minus c. Okay, so in terms of graph, sine t, of course, you know very well that is a sinusoidal graph. Okay, so now of course the graph is a wave, and of course it's having phase angle. Okay, so this is ut of pi all over 2. So this is actually going to be the interval at this point. This is the point where the function actually turns on. So this is the graph of sine t, and of course you know very well that in terms of radians, this is pi. Okay, all right, and of course this is 2 pi. So since the function actually turns on at pi all over 2, so this is the point. Pi all over 2 is at this point. This is the point of pi all over 2. So now, passing this particular function through a unit step, you know exactly what is going to happen. All the part of this graph, starting from the origin to this point, will be cut out. So of course, let me use a dotted line to represent that. Okay, so the only part that will remain is going to be all the way, all right, forward. So which simply means that if we have a graph of sine t is actually a graph, okay, that actually starts from the origin. That simply means that the phase angle is actually 0. Now you actually step it or pass it through a unit step function. It's going to step the phase angle, all right? the angle from the origin 0 to a point, to this point, which of course is pi all over 2. So it is going to step it forward. Okay, so this becomes the graph. So now what we see here now becomes the graph of course, of sine t, the u of t minus pi all over 2. So please take note of that. All right, so that is it. So what is really very important for us to understand here, okay, apart from understanding the effect of the unit step function on different function, and of course their graph, we need to also know how to apply Laplace transform of a unit step function. Okay, so let's do that. So let's look at the Laplace transform of unit step function. Okay, so what is the Laplace transform of a unit step function? Now picture the Laplace transform of a unit step function, that is L of u of t minus c. Okay, let me just put a constant. Okay, just picture this as the Laplace transform of A, but with a shift. Remember, we treated the shift theory. Okay, applying a shift theory of t, right, being equal to c, a shift of c. Okay, so invariably now, you know exactly how we do that. So invariably we can actually write this way. So we can say this is actually the Laplace transform of the coefficient of A, then multiply by the shift. And you know our shift theory, okay? So this, of course, shift is the exponent of minus the shift. The shift we have here is c minus cx, okay? So now exponent of minus cx, we now have to apply the Laplace transform of A. What is the Laplace transform of a constant? That is going to be A all over x. Okay, so please take note of that. So invariably, anytime you are being asked to evaluate the Laplace transform of a unit step, okay, you are looking at the Laplace transform of that function, but with a shift, applying a shift theorem, okay, of that time to which that particular function is turned on. I hope that is well understood. So invariably, in the case where here I'm having in the case where it is just the Laplace transform, okay, the Laplace transform of just u into t minus c, okay. So in this case now, you know very well that the coefficient is 1. So this is also is equivalent to the Laplace transform of 1. Then of course multiply by the shift of minus cx, which is equal to Laplace transform of 1 is 1 all over x, right? That is exponent of minus cx, then multiply by 1 all over x, which of course is, if I multiply by 1, I'm going to have exponent of minus cx, then of course divided by x. I hope that is well understood. Okay, so we can also go further to applying applying t, all right, to what I have, all right. Okay, so let's say this is t, the function is t this time, not a constant. So invariably we are looking at the Laplace transform of t, then multiply by the shift. Okay, So please take note of that. The Laplace transform of t multiplied by the shifts, and which we know already that the Laplace transform of t is, of course, t is raised power 1, that is 1 factorial. 1 factorial, which of course is 1, then divided by x raised power 1 plus 1, that is s raised power 2, which of course is exponent of cx, exponent of minus cx, then divided by s squared. So there is no much difference, okay, between what you are doing here and what we've actually accomplished previously. So what you are basically doing is to apply a shift to the Laplace transform of a function. So I hope this foundation that I've given you is good enough, because we're going to be looking at some more example of Laplace transform of unit step functions, okay, or functions that has been supplied, or that have been applied, okay, to a unit step function. And of course we're going to be also be looking at the inverse Laplace transform. So that is it. This is what we're going to be looking at in the this is what we have for this video. All right, so in the next video we're going to look at more example. Okay, so see you in the next video. Thank you very much.